This is part 2 of machine learning for image reconstruction. We'll go into a couple of examples of direct image reconstruction and then look at unrolling iterative reconstruction in order to put machine learning or deep learning inside iterative image reconstruction. Just a quick mention of the paper from which I'm taking a few figures for this presentation, as also for the previous video. So first then, let's take a look at DeepPET, the method of Hagstrom et al., which basically uses a convolutional encoder-decoder where a sinogram, a 2D sinogram, is basically taken through a whole series of convolutional layers, but crucially there is this spatial downsampling into this compact latent space, followed by these convolutional layers that seek to do a decoding of the information in that latent space. So this downsampling is the encoding, where basically we're taking this spatial information and placing it into this latent space, and then this upsampling corresponds to the decoding, and again this is using convolutional layers in order to express the information in that latent space in the form of a 2D image in this case. And so here I've just got a color code for the different size kernels used in each of these convolutional layers, and on the top here we've got the number of kernels of that size that are being used, which corresponds to the number of feature maps at each stage here in the downsampling and also in the spatial upsampling. Now it's worth noting here they use 200,000 training data pairs and we're learning 60 million parameters. So this is a really major enterprise to do this, even though it's only just for 2D image reconstruction. They use simulated data for the training, and they reported a reduced noise compared to OSEM reconstruction, and importantly here as well, 100 times faster reconstruction than OSEM because it's a direct mapping from sinograms to images. Another well-known example, this was primarily shown for MR, the method of Zhu et al., published in Nature, where they have a case space, a 2D case space, 128 by 128, being mapped to a reconstructed T1 weighted brain image, for example, here of size 128 by 128, again a 2D image reconstruction. Here they take the 2D case space, these are complex values, and so first of all these are reshaped into a very tall column vector for then insertion to a fully connected layer. That's a full matrix that's being learned there. Followed by a hyperbolic tan activation, then another fully connected layer, followed by yet another nonlinearity, hyperbolic tan activation. And then when they're here, they now reshape that very tall vector into a two-dimensional image, ready for being put into this series of convolutional layers of varying numbers of kernels, or rather the same number of kernels, 64 kernels in each of these convolutional layers. But they do change the kernel size, starting off with 5 by 5 and then progressing to 7 by 7. And then this all needs to be glued together at the end to deliver the reconstructed image. And so here they've got 50,000 training data pairs learning a colossal 800 million parameters for this 2D reconstruction. They did try out training on brain data only, and that delivered the best results because obviously this network ends up learning the manifold of the T1 weighted brain images. But to be more general, to improve generalization, they also tested on training on natural images and even on random noise examples, which would be the most general case. But of course the best results were for when they trained on the brain data. So they reported reduced noise and reduced artifacts compared to conventional reconstruction, and the RMSE was almost halved, in fact, compared to regular reconstruction from undersampled data. I'm showing here the example of fully sampled. I think they were mainly focused on looking at undersampled trajectories, so don't be misled by that pattern on the left side there. Obviously faster reconstruction, and they also demonstrated this for PET. Now it's important to say that these fully connected layers early on here would effectively, for the case of MR reconstruction, be doing something like an inverse discrete Fourier transform, albeit from undersampled data, so imagine missing parts in that case space. Whereas when demonstrated for PET data, this effectively would be learning something like the inverse radon transform, something comparable to filtered back projection, but obviously with optimization of the level of smoothing required according to the noise in the data. So here's a comparison of direct methods for PET reconstruction. So I've included DeepPET and AUTOMAP, the two examples that we've just taken a look at. And you can see that they're characterized by this very large number of parameters that are being learned. First of all, DeepPET with the convolutional encoder-decoder, and then for the AUTOMAP case, it's those fully connected layers that are really ramping up the number of parameters that need to be learned. These used mean square error loss functions. There was an L1 penalty for the parameters during the training of AUTOMAP. But notice also these are 2D reconstruction methods and need colossal amounts of training pairs. There are other methods out there, and perhaps the one on the bottom is worth noting because they didn't use quite as much training data and they were beginning to get into 3D reconstruction, but still a large number of parameters. This third row here is similar to DeepPET, but they added on an adversarial network to provide a discriminator, and they also had a perceptual loss included as well. So far then, we've looked at direct reconstruction methods. So they're making no assumptions at all. They're even learning things like the inverse radon transform or the inverse discrete Fourier transform. They use the raw data and they are fast. On the other hand, though, they are ignoring accurate models that we're pretty confident about in terms of the imaging model or even the statistical model for the case of PET, where we know it's Poisson distributed. And also the other downside really with the direct methods is the large amount of training data that they clearly need. We're looking at well over 10,000 training pairs and training 10 to 100 million or more parameters. And then in the previous video to this one, we also looked at post-reconstruction CNNs, and they were relatively easy to train and use. However, they don't access the raw data, and there's a query as to how much of the information has actually been preserved and kept in that reconstructed image. I'll show some results later on in this presentation for using a UNet post-reconstruction, and perhaps there is room for optimism. But nonetheless, ideally, we'd like to use our knowledge of the system matrix, use our knowledge of the physics, and also knowledge of the noise distribution, so that's the Poisson distribution for the case of PET imaging. We'd want to access the data directly and yet use that machine learning concept, that benefit of not fitting to noisy data, but instead training a mapping that takes us to a very high quality reference or the ground truth, even if we do have it. And also we want the methods to be practical for 3D with not such high training data demands that we see in those direct methods. We'd want to be dealing with maybe tens of images rather than tens of thousands of training pairs. And so that's why we're now going to talk about unrolled iterative methods, as these are a way of effectively achieving that list of ideals that I've just mentioned there. And basically they're putting convolutional neural networks inside iterative image reconstruction algorithms. I include on the bottom there a list of 3 key references, even 4, that have done this very thing for PET, but I'll also be covering the method of Hammernick, who really did this quite early on with variational networks for MR imaging. So first of all then, let's quickly look at the iterative method, the EM method for PET data. This is a very well-known core methodology. It's basically a forward projection of your image, and then you take a ratio of the measured data, back project, multiply and divide by a sensitivity image, which is just A transpose 1 here, and that gives you an update of your reconstructed image. So imagine here then we've got this nice clean noise-free measured data. We'd have maybe 1,000 such sinogram data like that for a 3D scan on this PET-MR scanner here. And then the MLEM algorithm would basically unfold as indicated there. We'd start off with a uniform image, forward project it, that's the AXN. We'd take the ratio with the measured data, that's here, back project it, that's A transpose on the forward projected. Sorry, so that's A transpose on the measured divided by the forward projected. And then this would be basically multiplied after normalization with the sensitivity image to get the next update. And so you can see we get this nice unfolding of the image as we go through the iterations of the EM algorithm. And this is effectively delivering an image that is really going to ultimately very closely fit the measured data, which is fine if the data are noise-free, but of course in reality we do have Poisson noise in the data. And so that's what I'm showing here, the problem of noise. First of all, without noise we get this nice crisp image. In fact, it would be much better than that had we carried on iterating, but the reason I haven't iterated more there is because if we had reduced counts due to reduced scan time or reduced frame length, reduced injected dose, then we would have Poisson noise on this data. And if we do 32 iterations of EM, we get quite a noisy result like that one. Or if we have even fewer counts, then things only get even worse. Hence, the idea of can we use those deep networks, those machine learning methods that we've looked at for post-reconstruction, that we've looked at for direct reconstruction, can we somehow include those methods into this kind of iterative image reconstruction? And so that's what we'll be looking at next. So this is called unrolling iterative image reconstruction. And basically, we're viewing the iterative reconstruction as a deep network. So we've got some input image. That's an initial image. Usually it's a uniform image, as indicated in those earlier slides for MLEM. It goes through that EM update process that I just illustrated at length in the last few slides. So the measured data comes into each of those updates, and then we end up with a final reconstructed image. Now the point is, as we've just seen, that would be a noisy image if the sinogram data were noisy. And so that's where there are conventional regularization methods out there for PET. So DeepPET is a good example of that, where what happens is during the sequence of iterations, you not only do the data-based EM update that I've just shown you, but you'd also do a very simplified denoising of that update in order to fuse it together with the data-based EM update to deliver the next iteration. And then we can keep iterating and then get a regularized reconstruction which will not be so well fitted to the noisy data, which is what we want. We want to avoid the reconstructions being too noisy. The problem is these kind of methodologies often rely on analytic, mathematically convenient choices of priors which influence this denoising process here, such as a quadratic prior, where this denoising is a very simple blurring process. And it's very unlikely that these kinds of methods are going to be optimal. So that's where machine learning or deep learning can really come in and help. So this is what, in fact, is done. This summarizes those three methods I mentioned briefly earlier, and I'll list them again in a moment in a table, but this is like a nice summarizing methodology. So I'm calling this a block, or really actually I prefer to call that a module, I think. But anyway, these blocks or these modules, we have the initial image coming in to a series of these modules or these blocks, and within each of these modules we have the conventional data-based update, and that's the EM method that I've just shown you explicitly, but then we'd also put it through a denoising update, just like we saw for the conventional map EM, but now that would be a learned denoiser, where what we've done at that stage is usually, in fact, to try and find a mapping that will take you from the way the image looks at that stage to try and map it to the high-quality reference, which could, for example, be found by using high quality, high stats data, even if you've got it, if it's possible, higher resolution data, or a ground truth if you've got the simulation. You'd use that high quality reference here to train that denoiser to take the iteration, the image at the certain iteration, to try and get that to agree with the high quality reference. And once you've done that learning of that particular mapping, I've called it F superscript N to show that it's iteration or module or block dependent. That is then inserted as a very simple prior for the conventional EM update, basically. Where it's basically constrained to be a map EM update, where I'll show you the update in a second, but basically we're just requiring a combination or a fusion of the data-based update with that deep learned update. So it's actually quite a simple procedure that goes on there. And when that's been done, in fact, it can be done a number of iterations, then we get our next iteration and we're ready to go into the next block to go to yet another denoising unit here, which could either be the very same one or indeed iteration dependent, which is what I've shown there by putting a superscript N for that mapping, showing that we've trained up a dedicated deep denoiser for every single iteration or every single module in this very long, this very deep rather, network. So here is a comparison of the various unrolled methods for PET reconstruction. On the top row here, I've got the method of Gong et al., which used a denoiser that in fact was module dependent, so it did have that superscript N in the mapping F. And so in fact that was, I believe that was basically a UNet type architecture. So it's still nonetheless a convolutional neural network. And they used mean square error for the loss function. And they importantly did do 3D reconstruction and needed a relatively low number of training pairs because we're not training quite as many parameters, and we're now dealing with 3D reconstructions as well. They did properly train this unrolled network, backpropagating through all the layers, including backpropagation through the EM update itself. And my understanding is that that would be a pretty memory-intensive procedure because you've got to have all of those feature maps and all of the backpropagation of all the gradients all the way through the entire network. So row 2 here is the method of Moranian and myself, actually. So we've only got 77,000 parameters there, use mean square error, 3D reconstruction again, 35 training pairs, and here backpropagation was done through all the layers, but this, important to say here, in fact it was the same network used for all the modules. So the backpropagation was done through the duplicated modules, and nonetheless a very memory intensive process. The backpropagation, though, didn't go through the EM update in that implementation that was published in TRPMS. And then finally to mention here the earlier method, as well as published later as well in TMI, of Lim et al. So there they've got 40,000 parameters in effect, and they've got the kind of module that's now iteration dependent, so sort of comparable to FBSEM-Net in that it's iteration dependent. So what I should have pointed out actually was that these first two methods look at the endpoint image that comes out of the entire deep network and try and get that to match the high quality reference. Whereas with the method here, the BCD-Net, or the iterative neural network as it's called in the TMI publication, they actually take the output of the current module and compare that to the reference. And so that is in fact a far more memory helping training methodology that's done at the module level. And so there are possible advantages in doing things in the way that are proposed there. Okay, so let's take a closer look at FBSEM-Net. So here we've got an example EM reconstructed image at a certain iteration number and a T1 weighted MR. These go in, so this is obviously an initial reconstruction that goes into this unrolled deep learned network. And what we have then is the conventional EM update. And here we have a few layers of a deep learned denoiser that takes the current update and it takes the MR image, learns what it would have learned what the regularization needs to be, such that when this regularized update is fused with the EM update, we get an outcome that goes into the next module and so on, such that that endpoint image needs to be a best match with the high quality reference. And I'll show you what those references look like in a moment. So mathematically then, each of these units is, in fact, for FBSEM-Net in the original version, is not iteration dependent. So it's just got one mapping F, which operates on the current image estimate xn to deliver a regularized update. And then we use the conventional EM update, which I've talked you through earlier, and so I'm just showing that explicitly mathematically. It's just the forward projection, ratio back project, multiply. And then what we do is this proximal operator, where we basically are looking to get the next update by doing the maximization of the Poisson log likelihood subject to the penalty that it shouldn't be too far from that regularized update. And so the entirety of that can just be solved by a nice straightforward MapEM update where we just have the regularized image as a prior. As you can see here, it's just like a prior that's just quadratic, very simple to implement. And this endpoint update is just fusing the data-based update with the regularized update. So quite a straightforward implementation. So if you test that method on simulated data, you get quite impressive results. So here we've got 10 to the 10 counts in the high quality reference. For OFCM, only about 10 to the 8 counts used here. Here it is OFCM reconstructed with PSF modeling. But then there's a conventional MapEM reconstruction using MR guidance, which is doing well. But I'm sure you'll agree that the last two columns here, which use deep learning methods, do the best. Here we do have a post-reconstruction trained UNet, and you can see in fact it's doing extremely well in comparison to the method that I've just described to you, which is FBSEM-Net, where we have that deep learned denoiser, the same one, included in every single module or block at every single major iterative update. And you can see that therefore that method on the right hand side compares very well indeed compared to the reference, and obviously greatly surpasses the image quality of regular OSEM. Here is the method now demonstrated on real 3D FDG data, and so here the reference is a 30-minute scan, and the lower quality data that were being reconstructed came from just only 1/15 of the data, so a 15th of the data. That's 2 minutes worth of data. And so here's OSEM, conventional reconstruction, compared to the post-reconstruction UNet and compared to FBSEM-Net. And again, the deep learned methods and hopefully FBSEM-Net just a little bit more maybe is comparing extremely well compared to the reference. But I think it has to be said the conventional UNet is still doing extremely well here. Okay, so now finally moving on to these kinds of unrolled methods for MR imaging. So now our measured data are going to be case space samples. I'm showing again a fully sampled case space, but in reality this would often be some kind of accelerated acquisition where we've got missing samples in case space. And because it's MR, we're doing a simple least squares based method. We're trying to find the X, which when forward modeled through A, and remember that's going to be your qual sensitivity maps, your Fourier encoding, your undersampling pattern. So basically X, when forward modeled to your case space, needs to agree with your measured case space data. And that can be done with some kind of gradient descent approach where you just take the gradient of this and then just have some step size to iteratively step towards an improved estimate, which will hopefully end up minimizing that objective function. So that's all very well and good, and again, if for the fully sampled case that's going to work well, but if this is undersampled, then there will be aliasing artifacts appearing there. So that's why there is a need to regularize, and there are advanced methods like compressed sensing where you do a kind of a random sampling pattern of some sort in the case space. Depends, there are various ways of implementing it. And then you also need to use this regularization. So basically this is composed of some kind of transformation of your reconstructed image such that when you transform into that space, you expect there to be a very sparse amount of data in that transformed space. So that could be, for example, there could be a wavelet transform, for example, as perhaps indicated there. Or you could be requiring that the image be composed of piecewise smooth regions, in which case some kind of gradient operator on here should give a sparse result. So any kind of transform that you might intuitively think should deliver an outcome that you'd expect to be sparse for images that you believe should correspond to what you're interested in. And then phi is just some kind of potential function. So traditionally that would be something like a quadratic, or it could be the absolute value. So for example, if k is some kind of difference operator and if phi is the absolute value, then that would be a total variation type of regularization. So the catch here is that these are, if you like, mathematically convenient transforms, or ones that are not necessarily optimal, not necessarily tuned to the kind of data that you're dealing with, and so they are unlikely to be optimal. So that's where a variational network comes in. This is a representation of the method of Hammernick et al. Back in 2018, where you have this same gradient descent based update. So here you see at the top level, you've got that conventional least squares with a step size, the least squares update, that's just that gradient of that L2 norm data fidelity term, step size lambda n. But now we have we're doing the process of learning now the regularization that is needed. The key difference here is in the regularization. So to understand that, first of all, look down here. You can see we've got the data-based update here, lambda n, with this is just the gradient of that L2 norm. And then we've now got the gradient of what we saw on that earlier slide, where we've got, in general, some potential function and then some transform operating on your data. Now here we're allowing a large number of these transforms, up to n subscript k of these transforms, and we've got the gradient that's been taken here. So that's why we've got the transpose of this matrix K, and then we've got the derivative of the potential function. And basically what the method of Harmonic is doing is learning the matrix K, where basically it's being replaced by convolution kernels, or not replaced, but simplified by using these kinds of convolution kernels. So K is a set of different, so Kn is a particular convolution kernel, and then they are learning the gradient of that potential function, which curiously can be kind of understood as if it's like an activation layer. So you could consider this as a convolutional layer with n different kernels, and then a lot of different activation functions here, and then basically the transpose of the kernels that were just learned here. So this then is a learned regularizer, and it's quite a shallow network. You could say it's just got one convolutional layer followed by another convolutional layer that doesn't have an activation after it, and where in fact the kernels in that last convolutional layer are just the transpose of the kernels here. So you're only learning one set of kernels and one set of gradients of the potentials, which can be understood as activation functions. So it's a very constrained form of a very compact convolutional neural network, if you like, that's being learned here. And that's being added on to this gradient-based update to then give you your next iterative update of the image. And so this succeeds quite well in reconstructing images that are from undersampled data. And I'll show you an example now from Claudia Prieto's group here. And so here, she's comparing the fully sampled reference acquisition on the right-hand side to then doing a multi-scale version of that variational network that I've just shown you. So it's not exactly the same, but this is a multi-scaled variant of that they did, and they presented this at ISMRM 2019. And so they do compare to compressed sensing, but here I just want to draw your attention to the kind of quality compared to the other methods that they get with the variational network shown in this column here. And you can see they've got a pretty good image quality compared to the high quality fully sampled reference. And furthermore, this is coming with significant acceleration, so that's only a 2-minute 34 acquisition because they've done 9-fold acceleration there. And they managed to do this reconstruction in only 14 seconds. And so that compares to a much longer acquisition time for the fully sampled data, of course. And it also compares, on the other hand, to a much longer reconstruction had compressed sensing been done for that 9 times accelerated data. So this CS would be also 2 minutes 34, but with a longer reconstruction, and perhaps with a result that is not doing as well as the variational network method with the multi-scale approach used here, where basically you've got a much faster reconstruction and possibly even a better image quality as well. So to summarize then, for these two videos, we know from conventional reconstruction, PET suffers mainly from noise. That's due to low dose or limited scanner sensitivity, short scan times, and so on. MR tends to suffer from aliasing artifacts due to quick acquisitions where you don't collect all the k-space samples. And so in both cases, mainly for different reasons, we do need to regularize. And when you regularize, you need to start choosing your priors, you need to choose your hyperparameters, and all of that is really open to a lot of optimization and tuning. And so this is where machine learning can come in, and by use of training data, we can optimize the choice of those priors and the hyperparameters. And and the paradigm then of machine learning is also a good one, which is to map noisy or the undersampled data to a high quality reference. The conventional methods do not make any use whatsoever of the ground truth or a high quality reference. And so I'd argue that's the real kind of paradigm shift in deep learning or machine learning based reconstruction. In the two videos, the other video and the one I'm just doing here, we've really now covered 3 main approaches. I started out in the first video going over convolutional neural networks for post-reconstruction processing, showing some of the nice progress made there. And then in this video, we've looked at direct methods as well as unrolled iterative image reconstruction. And I think there's going to be a great need to do a lot of comparisons of performance of all of these various methods. Thank you for listening.